So once again, let us proceed. And today we are going to start on the types of radar systems. And for the first time, we're going to have block diagrams that actually are able to describe the different types of radar. So the first radar we're going to handle is the continuous wave Doppler radar system. And this is the block diagram that we expect to have in terms of the operation. So in this type of radar system, the transmitter oscillator frequency, the transmitter oscillator, the continuous wave transmitter oscillator produces the frequency, and as it sends the frequency to the antenna for radiation, equally the transmitter sends another frequency similar value to the transmitter mixer. So from the transmitter mixer, it gets out, it is mixed with an IF oscillator to produce an RF, produce the output that is taken to the receiver mixer. So the difference between the signal received and the signal transmitted, and this is F of the signal transmitted, is now amplified, and is now amplified, detected, and actually transmitted to the indicator. So whatever we need to understand is that in this continuous wave Doppler radar, the continuous wave transmitter produces pulses continuously. But at the same time, the transmitter mixer has to feed to the receiver mixer so that we get the difference that is actually detected and amplified to indicate the position of the radar. So we are going to understand this. So the continuous wave transmitter oscillator transmits pulses, but as well sends the pulses to the transmitter oscillator. So the transmitter oscillator output is fed to the receiver mixer. And the output of the receiver mixer is amplified and detected and displayed by the indicator. So this is basically what we need to know. And another thing we now come to understand is what is the advantage of having this type of the continuous wave Doppler radar. So we're going to have the advantages. So number one is lower power consumption. Another thing is the simple circuitry. When you look at this, we have the transmit and the receive on a different path, and because of that, we are able to have very less power consumed, given that we have got different paths of transmission and reception. And another, the circuitry is very simple. It appears to be very organized and easy to follow in terms of the signal flow. Number three is that less bulky equipment. So this, as we compare with different types of radar systems, shall be able to realize that. So number 4 is accurately measures relative velocity. Accurately measures relative velocity. And lastly, number 5. So with the little modification, the CW radar, CW stands for continuous wave radar, can be used to measure or indicate the direction of the target. So we are going to talk about also the disadvantages. So number 1 is maximum power transmitted. It's limited by the range of the radar design. Another thing we don't talk about is, so this type of radar is easily confused by the presence of large, of large and whatever referred to as large objects near the large objects near the receiver. And lastly, number 3, what we talk about is this. It cannot indicate the range of the target. So we are also going to look at the applications. Applications of CW radar. Number 1 is rate of climb meter. In take-off planes. And number 2, what we have here is aircraft navigation and speed indication. Aircraft navigation and speed. Aircraft navigation and speed measurements. Application number 3 is radar speed meters in police. Radar speed meters in police monitoring. So let us take note of some to this. So CW radar transmits continuous pulses. transmits continuous pulses. Transmits continuous pulses. Continuous, not pulses, sine waves instead of pulses. Sorry for that. Continuous sine waves instead of pulses. Instead of pulses. Another thing we note at that is CW radar uses a Doppler effect. Doppler effects. It uses the Doppler effects to detect the targets and the range. To detect the target. So basically, this is what we require to know concerning the CW radar. So we're going to go to the second type of radar. So we now have to get space and do something rubbing. So this is a second type of radar system, and we look at this is frequency modulated. With frequency modulation, then you are able to measure the range of the target and not just detection. So another thing we need to understand is that because of that, it's more advantageous than the continuous wave radar. And because of that, we are able to, having the capability to measure the range, then it gives us easy work in terms of knowing where the target is so that we can be able to track it very easily. So this is basically what it is. And when you look at this, the transmitter oscillator, and the mixer, the receiver mixer here. Sorry for this arrow. This arrow is supposed to be, when you receive the signal is actually, the mixer is split into two. One is going to the transmitter oscillator and one is going to the amplifier for the detection. So when you look at this, the sawtooth generator is because of the easiness of modulation. That's why we use the sawtooth generator. And it's modulated so that we can now have the range detected very easily. So from the sawtooth generator, we go to the frequency modulator, then we go to the transmitter. But equally, the receiving, this is meant to be able to give us a different signal so that we are able to transmit the actual signal that we are going to get to the target range. So the output of the receiver also is given to the amplifier and the limiter. This basically is to control, to prevent the unwanted signal from being produced in the counter. And the frequency counter will help us determine the amount the range in terms of the time, in terms of frequency, so that we're able to use that to determine the time taken for the signal to travel for us to get the signal, to get the range of the object. The indicator basically to show us where the object is in terms of the actual figures in range. So it's able to determine the range. It's able to determine the range of the target. Another thing is that the carrier is frequency modulated. The carrier is frequency modulated. It's frequency modulated, and therefore it's easy to distinguish one cycle from another. One cycle from another. Another thing we want to look at this, when you see this, it's used as a sawtooth generator, and the reason is because of the simplicity. The sawtooth generator is used because of its simplicity, because of its simplicity. during modulation. So another thing, so if the target is stationary, the target is stationary with respect to the plane, a frequency difference is used, the frequency difference proportional to the height of the plane. The frequency difference proportional to the height of the plane is used to determine the range. So another thing is that the output of the mixer gives the frequency difference, which is amplified. The output of the mixer gives the frequency difference which is amplified, and band limited. Unlimited, then fed the frequency counter, which is amplified and limited, then fed. Then fed to the frequency counter that is calibrated and indicated. The frequency counter that is calibrated, in meters. So basically, this is what we have as this. So shall we be able to determine also the advantages of this type of radar system? So advantages of frequency modulated CW radar. The first key thing you need to know is that it can be able to measure range and velocity of the targets. It can measure range and velocity of the targets. And advantage number 2 is that it's able to use small antennas due to its size. It's able to use small antennas due to its size and proximity to Earth, proximity to Earth. Advantage number 3, equipments are less bulky. So you shall also have disadvantages. So we talk of also the disadvantage. So basically, we have one. It requires disadvantage it requires. It requires greater bandwidth. That's the main disadvantage that it is done. It requires greater bandwidth than CW radar. This is basically because of the modulation that it uses. Then we're going to talk also of application. Where do we find this type of radar system? So in terms of application, we also have what I refer to as the altimeter, radar altimeter. So we're going to have the third type of radar system. So this is our third type of radar, and basically it's a pulse. The meaning of pulse is that it only works during the period that the pulse is being transmitted or received. So another thing that is coming again in this drawing is also the plexer. And the plexer is a device that's able to allow us to use a single antenna for transmission. And in particularly, it's able to connect and disconnect the transmit and the receive path. And therefore, it's able to separate the transmit and the receive path equally. So we have the trigger. The trigger will give us the triangular wave pulses. But those triangular pulses, when passed through the modulator, they'll be transformed to be rectangular. So the output of the modulator will now switch on the tube at appropriate times, on and off, and we'll switch on the tube turn on the tube on and off at the required time when we are connecting through the transmit, the plexer switch. So equally, the RF amplifier will be connected because the duplexer is able to give us to connect the transmitter and the receiver at different times. So the RF amplifier will be connected at appropriate times, and the output of the IF amplifier will be amplified and detected and video amplified before we connect to the indicator. There's a key thing that we are seeing in this diagram is that there's a connection between the antenna and the indicator, and also the trigger and the indicator. So at any one time we are triggering and we are using this type of radar system, the antenna's ground is connected to the indicator and also the video amplifier and the trigger switch. So the trigger switch will enable us to have synchronism between whatever we detect and whatever the indicator will be able to show in terms of the diagram. So we have here that the trigger source provides triangular pulses. The triangular pulses which are then sent to the modulator. The modulator changes the pulses to rectangular waveforms. Changes the pulses to rectangular pulses. So that the output tube is turned on and off. So another thing you not know that equally the trigger source sends the pulses to the indicator so that there is synchronism. There is synchronization of the indicator and the indicator and the video signal. So another thing you need to know is that the receiver is connected at appropriate times. Is connected at appropriate times. It's connected at appropriate times through the duplexer. Through the duplexer. The RF amplifier amplifies the received signal and basically it is a low noise amplifier. The output of the mixer, the IF amplifier, the output of the mixer is fed to the IF amplifier. And is detected and video amplified, is detected and video amplified. Before it is connected to the indicator. So once again, let us resume our classes, and today we are going to discuss another type of radar system that we refer to as moving target indicator. So one of the things that we need to understand is that the basic principle of this MTI radar is that it uses two oscillators, the Doppler and the coho oscillators. Another thing is it also uses the Doppler's effect. We shall be able to discuss the Doppler's effect shorter in several episodes that are coming. Another thing I need to also to understand here is that the principle is that they are able to combine two frequencies. So one of them is the coho oscillator will be able to produce a frequency that is in the intermediate frequency, while the Oscillator oscillator will be able to give us a local oscillator frequency, or which is not referred to as stable frequency. So the two are combined in the mixer 2 and sent to the transmitting path. But equally, on the phase sensitive detector, the coho sends to the phase sensitive detector so that we are able to have the detection as required. But there's a delay line that's created so that we compare the actual signal and the phase signal when they're being processed. So this is basically what we refer to as an MTI radar system. So the key principle is to understand that there's a coho oscillator and the Oscillator oscillator at this point here. Then whatever you also need to know this is what are some of the things that we shall be able to compare with. What are some of the advantages we shall be able to compare with as compared to other types of radar systems. So let us proceed. So it uses the Doppler's principle. It uses Doppler's principle. Or the Doppler's effect. Another thing is that the transmitted frequency is the phasor sum of the output of the two oscillators, i.e. what I refer to as the Starlow oscillator and the Coho oscillator. So the Starlow oscillator provides the local frequency, while the Coho oscillator works on the same frequency as the intermediate frequency. So when you look at that, we also need to know that when you look at that, you also need to know that we need to feed a reference signal. Reference signal from the Coho oscillator is fed to the phase sensitive detector, so that we are able to have a comparison of the actual signal directly, and when the signal is passed through a delay circuit at the subtractor, so we get an actual video on the real time required. So the pulses that respond to the stationary objects are able to be identified, and with the delay time, we are able to synchronize the pulses or the signal identified using the subtractor there. So the output of the phase sensitive, the output of the phase sensitive detector is fed to the delay line and equally amplified directly before it's connected. Before it is connected to the subtractor. So the delay line attenuates. The delay line attenuates whatever referred to as the amplitude of the signal here. The delay line attenuates the amplitude of the signal, and so the signal must be of the same phase with the one that is connected directly to the subtractor. The delay line attenuates the amplitude of the signal so that it is of the same phase and amplitude with the signal fed directly to the subtractor. So basically, this is what we have there. So that comparison is done as a subtractor, and the output of the video, the output of the MTI video output is fed actually to the indicator or the display unit that we have discussed earlier, that referred to as the S-scope or the S-scope, the types of display units. So we are going to be able to talk about the blind speeds, which this MTI uses as the principles. So let us talk about something on the blind speeds. The blind speeds. Then what do we think? What do we have in a blind speed? The blind speed is a situation whereby the velocity corresponding to the target must provide us a phase difference of 2 pi radians between two successive pulses. During the scanning process in radar system, we send successive pulses, and we should be able to differentiate between one successive pulse and another one. So for us to be able to differentiate between one pulse and another successive pulse of similar character, we must be able to get a phase difference of 2 pi. And that one is only enabled in MTI radar using the blind speed principle. Then what is the blind speed? It is the radial velocity corresponding to, it is the radial velocity corresponding to a target having a phase difference, corresponding to a target having a phase difference of 2 pi radians, having a phase difference of 2 pi radians between two successive pulses. Between two successive pulses. So blind speed is given by where n is any integer, and this is the wavelength, or referred to as wavelength of the transmission. Then we have the FR, whatever as referred to as FR as the pulse repetition frequency. Pulse repetition frequency. So n is normally 1, 2, 3 to an nth number. So when we're talking about the lowest blind speeds, then the n must be the integer 1. But if we have got second lowest, or something referred to as second lowest, or what referred to as the second lowest blind speed, or the third lowest blind speed, the n normally changes according to the integer that is represented in the equation. So this is what we normally have. For application of these questions, kindly refer to the website, and I'll ask you to follow us mostly on the website for you to have some worked examples and questions and how they're done. Receive F1. So this is a DME radar, which is a fifth type of radar, and in this case, the interrogator sends whatever referred to as periodical RF pulses, which are received by the transponder. So you normally have that is the direction of the interrogation to the transponder, and the transponder also sends back to the receiver of the aircraft, so that we are able to determine the range of the aircraft, and the aircraft is able to determine which position we have the landing stations, or refer to the radar and landing stations. So the signals being received are amplified and modulated, and again amplified and modulated when the F2 with the F2 receiver. So this now comes. We have that direction. So that's basically a DME radar. Mostly you find this in aircraft navigation and aircraft movement. So the airborne interrogator sends periodical RF. The aircraft interrogator sends periodical RF pulses. Sends the periodical RF pulses, and these pulses, RF pulses are at a frequency F1. F1 to the transponder. So the signals are received in the transponder by the transponder. The signals are received amplified and again modulated and modulated, then send back to the aircraft interrogator. And then send back to the aircraft interrogator. So we send the signal from the F1 to the transponder. The transponder is able to amplify and modulate and send it back to the interrogator. So the signal is received by the receiver at the interrogator, and the received signal from the transponder is amplified, and the range of the aircraft is displayed So basically this is what we need to understand concerning this. So that range is determined by the distance between the ground and the display unit based on the whatever we talked as S-scope display, or the other type of display that discussed. So these displays will just be determined from the point of the origin of the signal to the point where there's a bright indicator or there's a larger beep from the display unit. So finally, we are going to talk about something. We're going to have something on. Doppler's effect. I'm going to have something on Doppler's effect. Something on Doppler's effect, and particularly, basically on how it's applied, and mostly it's applied on the CW radars that we have just discussed before. So Doppler's effect is the shift in frequency of an echo signal resulting from either the source or the target, of either source of oscillation or the target being in motion. Is the shift in frequency of the echo signal. It is the shift in frequency of the echo signal resulting from either the source or the object in motion. It is given by delta t multiplied by the wavelength, where that refers to the Doppler shift in frequency. Doppler's frequency shift. The d is the distance. T is the time taken. And that one is the wavelength. This is the time taken for scanning, that particularly for scanning. And this is the wavelength. So basically, for more information, let us meet. Just log into our website and get the applications of these formulas so that they do not appear as they are very new. But basically, this is what we will be looking at and apply the questions in the near future, or very soon we are going to be meeting when I'm discussing these kind of questions.